code still? So I will be going over the code myself as well. So if you don't have MATLAB or Octave to run the code, or if you don't have the code, don't worry. You are still going to get something from this course. And the code is going to be available online, so you can later download it and use it. But still, just one last time, is there anyone that wants to have the code now? OK. Can somebody give the code to Zubin, please? OK. All right, so Peter did a very nice introduction to Bayesian nonparametrics and to Dirichlet processes, and this is going to be a semi-practical course about the Dirichlet processes. So I'm going to be using the code from Whye, which hopefully all of you by now have. And what you need to do initially is basically change to the code directory and run init path to initialize the path. And then throughout the lecture, I'm going to show you different demos so you know what part of that toolbox is used for what. So as Peter was talking about, the Dirichlet Processes is a tool for defining Bayesian nonparametric models. And there are other well-known processes in machine learning for defining, again, Bayesian nonparametric models, like Gaussian processes, which we'll be talking about tomorrow, Indian buffer process, which Peter talked about, and Kingman's coalescent, which I talked about yesterday. So, but the focus now is on Dirichlet processes. So the Dirichlet process is basically a distribution over distributions, which you can use to represent your uncertainty about the parametric form of the distribution that you want to use in your model. So the typical thing to do would be, in a Bayesian parametric setting, would be to have a bunch of parameters for your model, and then represent the uncertainty about the value of those parameters in terms of some parametric distribution, let's say a Gaussian distribution, but you don't know the value of the parameter, so you would put a Gaussian distribution on top of it with some mean and some covariance, and you would try to get the posterior of that Gaussian when you do inference. Whereas with the Dirichlet processes, instead of putting that Gaussian, you're putting a Dirichlet process with a certain base distribution on the distribution itself, so that you not only learn the parameter, but also learn the kind of the parametric form, or like roughly the form of the distribution itself as well. So this is something a little harder to understand. You need to get used to the idea of using Bayesian nonparametrics to understand it. This is a very simplistic way of thinking about the Dirichlet process, basically as a glorified Dirichlet distribution. Glorified because it's over infinitely many dimensions. So because the Dirichlet distribution and the Dirichlet process is very closely related, I wanted to go over the basic properties of the Dirichlet distribution. I don't know why this keeps changing. Now it's a spoiler. So the k-dimensional Dirichlet distribution, we write like this, is the Dirichlet distribution with parameters alpha 1 to alpha k. Over this vector that is k-dimensional, pi 1 to pi k. So we denote the distribution like this. And the distribution is defined like this. So the indices of this vector, or the entries of this vector, are non-negative, and they sum to 1. So this I use to denote the probability simplex, the k-dimensional probability simplex. So the scale of the Dirichlet parameters, these alphas, determines the concentration of the probability mass on the probability simplex. For example, sorry about that. So if you have a Dirichlet distribution with parameters 1, 1, 1, then you have this kind of a distribution over the simplex. So it's a uniform distribution. If you have...
It's on slideshow mode, maybe?
I'm not sure. I just said play from start, that's it.
I think it plays the slideshow if you do that.
What do I need to do?
Try and view, maybe.
View. I don't know. I mean, that's what I used yesterday as well. Okay, I'll just do full screen then, if I can.
Enter view, maybe?
Zoom, enter full screen.
Now use the one at the bottom, down the bottom left there. The third
Ah,
one.
okay, this one.
I don't think that'll
Let's hope that it's only going to be for those bunch of slides, and let's hope that I just meant it to be that way. So I'll give you the summary before it starts scrolling again. So these are the parameters, and if so, we have k parameters for the k-dimensional Dirichlet distribution, and if all these parameters are equal, we call this a symmetric Dirichlet distribution. You have probably heard of this when talking about the Dirichlet process. Of course, it doesn't always have to be equal. Depending on your modeling needs, you may set these parameters differently. But just for now, let's look at what happens when you play around with the scale of these parameters. So these are values where maybe I can just pause it. Okay. So these are the density distribution densities with parameters 2, 2, 2, 5, 5, 5, 10, 10, 10. So you see that as you increase the scale of the parameters, the distribution gets more and more peaked. Note that these are all greater than 1. So it's interesting to see what happens when things are, I will pause it. Things are greater than, smaller than 1. So when the parameter is smaller than 1, then rather than getting concentrated on the center of this triangle, the probability mass starts going towards the edges. And the more you decrease the values away from 1, the more concentrated around the edges they become. So this is an interesting property for the Dirichlet distribution. And this is basically, these are basically what it looks like when you have different values for when you don't have symmetric Dirichlet. But the slideshow doesn't really want you to look at it very long. You can play around with the Dirichlet distributions by using the DIRdensity.m. You don't need to do that now, but this is basically going to show you what happens when you input different parameter values and so on. So the Dirichlet distribution, again, has an interesting property where if you combine entries of a Dirichlet distributed probability vector, you will still end up with Dirichlet distributed vectors, but with less number of dimensions this time. So if we have a k-dimensional vector, pi, that is Dirichlet distributed with parameters alpha 1 to alpha k, and if we simply sum up the first two entries of this vector, and similarly sum up the first two parameters of this distribution, this is what we get. So the vector with one less dimensions is still distributed with this Dirichlet. This time, all the parameters the same, except for this first parameter being the sum of the first two parameters there. And this is not specific to, of course, the first two dimensions only. You can do it for any dimensions. And the converse of this is also true. So you can have parameters, vector of k dimension, being Dirichlet distributed with alpha 1 to alpha k. if you sample these T1, T2 values from a two-dimensional Dirichlet, which is also called a beta function, a beta distribution, and then you multiply the corresponding entries with the corresponding values, like this, pi1 times tau1 and pi1 times tau2, similar to alpha1 times beta1 and alpha1 times beta2. I think there's a typo there. Making sure that this beta1 plus beta2 is equal to 1, then you get a Dirichlet distribution. So you can run dpgenerate to see that we can actually draw from a Dirichlet process by using this property. So we start with a uniform distribution over 0, 10. Therefore, this is at 0.1. And we keep refining by drawing from this beta distribution. We keep refining this space like this, for example. So when we first draw from the beta distribution, it divides it into two parts. And the height of that is proportional to the values that we draw. And then we'll keep recursing on each of these halves, like this. And if we do it long enough, we're going to have something like this. So eventually, you're going to have infinitesimal intervals, some of which will have huge spikes, and most of which will have tiny spikes. So this is a very easy and fun way of obtaining a draw from the Dirichlet process, actually. It shows you that you can get it as the infinite limit of the Dirichlet distribution. Okay, so there are different ways where you can define the Dirichlet process. You can construct samples from the Dirichlet process, or you can sample from the Dirichlet process. And one way to do it is by using the stick breaking construction. So if you go to the code, the sbgenerate.m code, it's going to generate sticks for you. So these are going to be sticks that are representative of these weights for the Dirichlet process parameter values. So the sticks are going to look like this because they are defined using this recursive formula where nu k is drawn from the beta 1 alpha distribution. In expectation, they're going to be exponentially decreasing. So these red parts are the stick lengths of the Dirichlet process. So these are going to be exponentially decreasing in expectation. Therefore, you're going to get to infinitesimally small values not very long from starting sampling. So here I generated some sticks, so with different alpha parameters. This is a good way of seeing the effect of the alpha parameter. So the alpha parameter of the Dirichlet process controls the expected number of clusters in the Dirichlet process mixture models, for example. You can say it also, the reason why it does that is it controls the distribution of these pi k's. So if alpha is small, then the pi k's will decrease much faster, and only a small number of them are going to have significant values. Whereas if alpha is larger, then they're going to, more and more sticks will have significant mass compared to others. But there will be still infinitely many of them with infinitesimal mass. So these are examples from alpha equals 1, alpha equals 5, alpha equals 25, and so on. And so in the previous slide, I only showed you the length of the sticks in the order that I sampled them. So we started with this, remember? So we started with a stick of unit length, and then we broke the stick here. We kept this as the first stick length, and then we recursed on this remaining part, broke it off here. This was the second stick length, and so on. And basically, I show here the sticks in the order that I draw them, these being the stick identities. So the first stick, second stick, 100th stick, and so on. Here, I'm showing it in a different way. I also sampled thetas from the base distribution G0. And now this is the value of theta. And these are basically the lengths of the sticks, the same lengths as before. I just wanted to show you that the alpha parameter makes the distribution concentrate more and more on the base distribution when it is larger. So that's why it's called the concentration parameter. To me, it first sounded counterintuitive that a parameter that has a value small, and if it has a value that's small, it leads to less number of components. So it sounds like it is more concentrated. The model is more concentrated. And when you increase the value of alpha, it gets more and more components. That sounds like it's a less concentrated model. But the concentration here is about concentrating on the base distribution rather than concentrating on like a few number of components. Okay, so as I said, you can run this code using the SB generate code. By the way, if there are any questions about the way to run the code or what is in the code, this is supposed to be a practical section, so just let me know. Another way to generate from the Dirichlet process is basically using the Polias-Earn scheme, which is different from the stick breaking construction. So here we don't have any pi values, so the pi values don't go into play here. We're directly sampling the theta values, and the way we do that is we start with theta 1 sampled from G0, and every consecutive sample is sampled by conditioning on that theta 1. And Gn denotes the collection of, basically it denotes the posterior of the Dirichlet process conditioned on the first n samples. So this is the form Gn is going to take, and Gi is going to be sampled from Gi minus 1, basically. So we iteratively sample. So the interesting thing about this sampling scheme is that Gn converges almost surely as n goes to infinity to a random discrete distribution G, and G has a Dirichlet process alpha G0 distribution, which means the collection of samples that you get, the sequence of theta I from 1 to n, is a sample from G. Okay, so here's an example of doing that. So we start with a base distribution like this, a Gaussian base distribution, that's G0. We sample from this, and we sample this location. So it's going to have some weight. Basically, its weight is going to be 1 over alpha plus n, and the weight of the G0 distribution is going to be alpha, like this. And then G2 is going to be including this, conditioning on this. We sample another point, and that gives us G2. And we keep doing this to get more and more samples. So as we increase the number of samples, this is what we get for G10,000. So this is a sample from the Dirichlet process obtained using the Polias-Earn sampling scheme. Okay? So again, about the concentration parameter. So if we have alpha equals 1, this is what a sample from the DP looks like. If we have alpha equals 100, this is what a sample from the DP looks like. So you can see again that for the case where alpha is small, the concentration parameter is small, the way the discrete distribution looks like is nothing like the base distribution, whereas the discrete distribution looks more like a kind of a discretized histogram of the base distribution. Just to re-emphasize that, that's why alpha is called the concentration parameter. Okay, so there's a fun interactive demo that you can also run. DPM interactive. Oops. This is basically, right now it's only the samples from the base distribution and an average of all the samples we have so far weighted more heavily towards the recent samples. So the blue ones are single samples and the black one is an average of all the samples. And this is a Dirichlet process with a conjugate Gaussian base distribution. So when we click on the plot, that means we add one data point, okay? At the red cross here, at somewhere close to 10, I added one data point, and you can see that the process is now focusing more on this point, so it's kind of peaking towards that, although there is still some probability of having other peaks away from that point. But if I just keep adding data points there, you see that more and more evidence is gathered, so the model is more and more sure about where the peak should be, right? If I now introduce other data, let's say some outlier data, which is away from this peak, it still has some information, right? It gives the information that there is not only one peak there, but there may be something going on here as well. So the samples are also getting peaked around that. But not as heavily as that, because this basically is overwhelming. But if I add more and more data points, now we see that it's focusing on a bimodal distribution, right? So you can have fun with this code, just clicking around to introduce more and more peaks if you want, or to join the peaks that you created like this to, again, go back to one peak or two peaks and so on. So it basically shows you that the Dirichlet process is a flexible tool that can flexibly adjust to new data. So you don't have to pre-specify the number of components. It's going to find the number of components that's necessary to fit the data. And as you add more and more data, it's going to be able to flexibly change to fit the new data. So let's compare the finite mixture models with this. So I'm showing here, again, a one-dimensional density fit for the finite mixture model, where by the red curve, I show the mean. By the dashed blue thick curve, I show the median, and then this is the 95% quantile. So you see, and all the rest is basically samples from the prior. So this is the prior distribution for a two-component finite mixture model. So if we observe data points that are shown by these black dots here, and we fit this two-component finite mixture model, we see that we get these nice two peaks around where the data lies, and the uncertainty of where these the probability mass should lie decreases. So compare the gray area here to the gray area here. So since we have more data now, we have less uncertain about what the model should look like, right? So it's doing quite a good job. So and we can see clearly that the data is clustered in two clusters. So this is a reasonable estimate. I actually generated the data from 2 Gaussians. But here I generated the data from 3 Gaussians. So the true model for this data would be a 3-component mixture model, whereas I used, again, a 2-component mixture model to fit the data. Now you can see that there is this gray area, which is a lot larger than here. So it's a good thing about the Bayesian framework that when there is uncertainty about the model that's learned, then it still expresses that uncertainty. So you don't need to discard Bayesian models altogether and migrate altogether to Bayesian nonparametrics. But basically, all it's telling you is it finds a bimodal distribution because that's all it can do. But there's high uncertainty. Okay? So it self-guides you by saying, well, I'm very uncertain about what's going on here, but it still gives you the model with 2 modes only. Okay, this is now the samples from the prior for the Dirichlet process case. So a Dirichlet process with a conjugate-based distribution, which is Gaussian distributed. And this is the fit to data that's generated from 2 Gaussians. As expected, you have these 2 peaks. And this is data generated from 3 Gaussians. And now you have 3 peaks. So this shouldn't be surprising because we know that the Dirichlet process is going to fit to the data, and it's going to use the necessary amount of components to be able to have a good representation of data. Okay? So you can see things like this, for example. There are peaks, if you sample from the posterior, there are peaks at places where there's not any data at all. So that comes because the process still gives some probability to other places than it saw data. So you may see this as an advantage or a disadvantage. If you believe that your data is only what you saw and there will be no other data lying outside of the region that you observed data before, then maybe this is something to worry about, and maybe actually this is a model that you shouldn't use then because you don't want all that flexibility. You want to constrain your model. But if you want to be flexible and give some probability to data coming from other regions, then this may not be such a bad idea to use this. Okay, so the infinite mixture model using the Dirichlet processes is defined by this. So we have a data point, or we have n data points indexed by I here, conditioned on some parameter, and that parameter defines the distribution of the data. And that parameter is drawn from some distribution G, which is drawn from the Dirichlet process with these parameters, alpha, the concentration parameter, and G naught, the base distribution. And this is a graphical model showing this, these equations, basically. So this is how we define the infinite mixture model. Equivalently, we can show it like this, where we have pi's and thetas rather than g's and rather than g's. We have pi's and thetas, where we basically represent G using this infinite sum that comes from the stick breaking construction. Okay, so given this model, how do we do inference on it? So typically, the easiest case to use these models in practice is to use a conjugate-based distribution so that the parameters can be integrated out and the predictive probabilities can be computed using the sufficient statistics of the data. So Peter was talking about 2 kinds of conjugacy. One is the conjugacy of the Dirichlet process itself. So the posterior process is still a Dirichlet process. That's one type of conjugacy. And that's always present in the Dirichlet process models. But at least the vanilla Dirichlet process models, let's say. And the other type of conjugacy is about the conjugacy of the parameters of the model to the base distribution. So if you want to model an infinite mixture model with Gaussian components, you need to specify a prior on top of those components, and that prior needs to be conjugate to the Gaussian distribution, because you assume Gaussian components for the data generating process. So what is the conjugate distribution for the Gaussian distribution? So if you're using both, if you assume that both mean and covariance is uncertain, that they're not known, then a normal inverse Wishart distribution is the conjugate to the Gaussian distribution. Or if you're fixing the mean and assuming only you want to learn the covariance, then you need the inverse Wishart distribution on the covariance. Or if you know what the covariance is, or you're pretty sure you can set it finally, and you only want to put a distribution over the means, then the normal distribution is the conjugate distribution for the normal means. Okay? And similarly, if you have discrete data, if you're using multinomial distribution, for example, to model your data, then the Dirichlet distribution is the conjugate distribution for the multinomial, so that you would use a Dirichlet multinomial model for that. Okay, so of course we're not tied to using conjugate-based distributions, but things become a little more tricky when you want to use non-conjugate models. And that's why here I'm going to be talking only about how to do inference for the conjugate case. So in Gibbs sampling, what you do at each iteration is for each data point, you remove the data point from its current component. So you start off with some random initializations of some initialization of a number of components with assignments of data points to different components. And when you start sampling, you remove the single data point from its current component. And if that component has become empty, so if that data point that you removed from the component was the only one that was assigned to it, you delete that component from the representation because nobody owns it anymore. And then you look at the conditional probabilities of the data point going to any one of the existing components or another new component. And you assign the data to one of the components looking at this conditional probabilities. Basically, you sample from a multinomial distribution with those probabilities. So what are those probabilities? Basically, they have components coming from the prior and the likelihood terms. So the probability of assigning to components for which there are more than 0 number of things assigned to, so going to one of the non-empty components, basically, is proportional to the number of things that belong to that component, except the data point that you're sampling for now. So this is what this notation means. So you take out the ith data point from the component that it belongs to. So it may have belonged to k or not. We don't know that. But if it is belonging to k, then we decrement n by 1. If not, we don't touch n. So this term is coming from the prior. And this is basically the probability of the data under that component. So how likely is it to observe that data given the component parameter? And the probability of assigning to a new component is basically proportional to alpha times this. So this is basically the probability of this data point under this Bayes distribution. So you integrate out all parameters using the Bayes distribution. Okay? So this is kind of coming from the likelihood term, and this is coming from the prior term. So we can do this for the components that have data associated with them because they already have some parameters that are assigned to them. And we need to do this. We need to integrate out these parameters because there are infinitely many of them, and we cannot basically, physically, we cannot consider being assigned to every one of those infinitely many cases, right? So this integral basically says I'm taking into account being assigned to any one of the possible infinitely many cases. Of course, this is proportional to how much mass the base distribution gives to those parameter values. So we can also do it a little differently. So rather than knowing the parameter values and conditioning on the parameter values to get the predictive value for that particular point under that parameter value, we can integrate this out given the posterior distribution, basically, of that component. So by this one here, I mean this is the probability of the data given the parameter. And basically, this parameter is going to have a distribution that is defined by the things that are the data points that are assigned to that component. So G minus I K theta here means it is somewhat like the base distribution, but it is like the posterior base distribution, which is conditioned on the data observed for that particular component. Okay, is that clear? Any questions about this? Okay. All right, so details about this code. Everything I'm talking about is implemented in DPM Gibbs.m. So we are given this raw cell vector of data items, and there are n many of them, n many data items. We set the alpha parameter. We decide on which hyperparameter to use, which value of hyperparameter, and we keep track of this. We keep track of the number of active clusters, the mixture components, basically, that are summarized by the sufficient statistics of the assigned data, because this code makes use of this form of sampling rather than this form of sampling, so it doesn't need to keep around the parameter values. And then the raw vector of cluster indicator variables and the raw vector of number of data items per cluster. Okay, so in detail, this is basically what the program looks like. We're initializing the parameters or the data like this. And then at each iteration, we remove each data item from the model and edit back in according to the conditional probabilities. So this is where we remove the data item from the component that it is belonging to. Basically, we retrieve its assignment, so it is assigned to Zi. Okay, so K is its current assignment. We subtract 1 from NK because we no longer have that component there. We remove it from there, and we also remove it from the sufficient statistics of this component, which is given by QK. Okay. So in doing this, we're kind of pretending like the component that we observe is in a sequence. If you think of the sequential sampling scheme, you have data points coming in, and you keep sampling from the Dirichlet posterior conditioned on all the previous samples, right? So in a way, when we're doing this Gibbs sampling, we're pretending like the data point that we observe is observed for the first time, and it is the last data point that is observed. So we observed n-1 data points before, and now we're observing one additional data point for the first time. That's why we pretend like it wasn't there, so we remove it from both the number of things that are assigned to that component, and we remove it from the sufficient statistics of that component. Okay, so once we do that, the model doesn't know about that data anymore, so it can pretend like it just arrived as the nth data point. And as I said, after removing the data point, we compute the conditional probabilities of the data item I belong to the probability of belonging to each component K. And this is some implementation detail. We compute the probabilities in the log domain and then take the exponential just to avoid numerical issues. Okay, so because some of these values can become very small and we don't want to always have 0 probabilities. Okay, so there's a small piece of code, log predictive, that actually calculates the predictive likelihood of this data under this component. Also in the package, so you can have a look. It basically evaluates what's the probability of this data given whoever else is assigned to that component. Okay, as I said, this is done for numerical stability, and this is basically normalizing the p's so that you can later on sample from it, using these as the multinomial distribution. Okay, so we sample the component by sampling from the conditional probabilities, and if a new component is added, which means if the data point chose to go to a component that nobody else was sitting at, then we need to instantiate the new active component by setting the number of things that it has and setting the sufficient statistics and so on. And then after instantiating, we add the data item back into the model by adding 1, basically incrementing the number of data items in the component K, the component that it chose to go to, and add the item to the sufficient statistics of that component that it decided to go to. Okay, so there's this part of the demo which you won't be able to do now because you don't have the data probably because you couldn't download, but I encourage you to get this later after you leave the island. Just not to...
Is it in the next data folder?
Huh?
Is it in the next data folder?
Yeah, but not everybody has it.
Yeah, so we will do that. Some people do that.
Okay, so there was a USB stick going around which has that data. If you get a hold of that USB stick, then you can copy that data and already start playing around with it.
Can you send that to the other gentleman?
But I just want to give you an overview of what data is about and what the model assumptions there are. There's already code implemented that does the modeling of this data, as well as the modeling of all the other, like the demos and so on that I showed you. But it would be useful if you try to do your own sampler so that you get a better feeling of what this sampling is doing actually. So this data represents each NIPS paper as a bag of words representation, which means the feature vectors are of the size of the vocabulary, V. Okay, so there are V words in our vocabulary. And paper I is represented by this vector that's of dimension V. And its entries are basically set to the number of words that occur, number of times a particular word occurs in that document. Okay? This data basically has a small subset of the papers and a small subset of the informative words to keep the data size and dimension small. So we can construct a Dirichlet process mixture model for this data. And since now we have a discrete distribution, we have words, right? And we have the number of words, so this is the discrete data. So we use a multinomial mixture to model the data. And of course, we're using the infinite mixture model. So as I said earlier, the Dirichlet distribution is conjugate to the multinomial. So we're going to use a symmetric Dirichlet distribution as the base measure, which looks like this. So this is the multinomial, and this is the Dirichlet distribution, basically, with parameter b, which is of size of the vocabulary. So this is what the model looks like. We have data generated from the multinomial. Sorry. And the parameters of the multinomial are sampled from G, which is a sample from the Dirichlet process itself, with this space distribution, which is Dirichlet, symmetric Dirichlet, with B over V. This is also a capital V. So this is basically a symmetric Dirichlet over the words in the vocabulary. So alpha controls the expected number of clusters here. Alpha is the concentration parameter, and it controls the expected number of clusters. And B, basically, this here, the parameter of G naught, controls the distribution of words among clusters. So remember the probability simplex I was showing you, depending on what the scale of the parameters were, it changed the distribution slightly, right? So if you had a larger scale, then things tended to concentrate on the center of the triangle. If you had less, then things were more diffuse, right? So this is basically what controls the distribution of words among the clusters. And yeah, try it out when you can. All right, so I think I'm going to take questions now.
Concretely, what is the number of scaling? So to read what the number of documents you can deal with such an approach of clustering? And the dimension of the vocabulary also.
Yeah, I'm not sure about the various implementations. I mean, I'm not sure about this implementation. There are people that have tried these things on large-scale data, and you can handle quite a large-scale data using this model simply because you need to only carry around the sufficient statistics. So because this is a fully conjugate model, but maybe Zubin can say what the scale would be for this kind of thing here. I'm not sure about this implementation. I didn't try it on large-scale data.
I mean, I think there are efforts to get these sorts of things running in parallel and things like that as well.
Yeah.
There's a lot of active research in this. But the sampling algorithms can be very efficient because they just do assignment of a data point to a cluster, and that's a very sparse data structure to represent. So it's sometimes more efficient than variational methods and things like that for a large-scale problem.
Yeah, especially for the multinomial Dirichlet case, I think. Any other questions?
Just a comment. I think alpha can be called the diversity parameter.
Well, the comment is calling alpha diversity parameter. Well, it's been called the concentration parameter. And as I said, there is a reason why people called it concentration. So. Okay, if there are no other questions, I'll show just a few more slides. And then I guess we have some time, right? Okay, so what I didn't talk about and what the code doesn't handle, the code that I've showed you doesn't handle is basically learning hyperparameters. So hyperparameters in this case is alpha, for example, or the B value for the multinomial that we assumed for the NIPS papers. So the value of alpha is very important for the type of model that we have, right? It tells you the prior expected number of components. So your result may change really a lot by assuming a small or a large value of alpha. So although in Bayesian nonparametrics we say we don't have the model selection problem because we do everything automatically, the number of things are set automatically by the model itself, there's still one thing to decide on, right? There's still a parameter that is alpha, which we call the hyperparameter, that kind of tells you that is also a choice of how many components you want to appear in the model. So it's not as rigid as the finite case, like finite mixture case, where you have to set k, and you're done with it. But you still need to think well about what you want to do with alpha. And one way to deal with this is, again, being Bayesian about things and putting a prior on alpha. So let alpha also vary with the data, right? So here I'm showing the number of components versus the number of data points. So this is the size of these squares tells you the probability of that combination. So if you have these many data points, if you have 20 data points, then having one component has this much probability mass, has two components having this much probability mass, and so on. So if you assume a gamma prior on alpha, then this is kind of what you get. Okay? So there is a heavy bias on towards the smaller number of components, but there is still non-zero probability of having larger number of components. So if your data supports it, you can end up with a large number of components. But there is something that is funny about this. So the probability diminishes really fast, right? So if you want to be a bit more secure about this, so you want a more uniformish distribution, then you can use an inverse gamma with, again, 0.5, 0.5 values, parameter values. And basically, this is the same plot, the number of components k versus the number of data points, and the size of these rectangles show you what the probability of each of those configurations is under this prior over alpha. Okay? So compare this to this. So you see that there is a more uniform distribution among these possible k values here. So again, there is no best way of choosing priors, but these are two possible things that I tried, and depending on your model needs, depending on your intuition about what you want to use for your data, you can choose to use this or maybe something else. Okay? So if you believe that your data probably comes from a really small number of components, but you still want to give some probability to a larger number of components, maybe you're better off using just a gamma. Whereas if you're not sure and you want to be more flexible about the number of components growing larger, then you may want to use inverse gamma. And one last thing, which again, I didn't talk about the implementation of, but which is about conjugate and conditionally conjugate, or conjugate and non-conjugate models, basically. So here by conditionally conjugate, I mean rather than having a parametric form that we can integrate out all the parameters, we have a parametric form where we can integrate out only some of the parameters, but we have to keep around the rest of the parameters. Okay? So if we try to model this data using Dirichlet processes, using a conjugate model that I showed you how to use in the previous slides, we get a density distribution that looks like this. There are three peaks that are kind of smooth. Whereas when you use a conditionally conjugate model, a model where you cannot integrate out all of the parameters, you can only integrate out some of the parameters and you condition on the rest of the parameters, you get a distribution that looks like this. So it looks less Gaussian, and you can see that it has more probability mass around these points, and that's probably because of these components being like outlying and pulling this towards here. And as a comparison, this is the kernel density estimation, or the Parsons window fit to the density. You can see that this is more grainy simply because what this model does is it assumes a Gaussian bump on each of these data points. So it is a non-parametric model, but not in the non-parametric Bayesian sense. So it's a non-parametric model in the sense that its complexity also increases with the number of data points, because it assumes the density this density is basically a sum of these Gaussian bumps that are n many of them if you have n data points. So you can see that this is a little too coarse, but then this is maybe a little too smooth. So maybe this is a better representation of your data. But as I said, it may be a lot harder to do inference on conditionally conjugate or non-conjugate models as opposed to conjugate models, both in terms of runtime, implementation, and getting a sampler to actually do correct sampling from. These are the statistics for this data, this data set, which is here. Basically comparing the the conjugate model and the non-conjugate model. You can see clear, and these are different data sets, so you can see why the difference comes about, right? So the conjugate model tends to use a lot less components. It's a lot more conservative in the number of components it uses as opposed to the non-conjugate model. Everything about these models were the same, all the parameter settings, hyperparameter settings, etc., except for the form of the prior distributions, form of the base distribution, basically. So you can see that there's a big difference between assuming a conjugate versus non-conjugate. And this is basically showing the number of data points assigned to each of these components. So there's a clear difference between that too. Okay, so that's it. I hope you get a better understanding of the Dirichlet process now. So I think the take-home message is, I think some of you don't. Anyway, the take-home message is they're not hard to use. They're very easy to implement for at least some cases. And they do give really good fits to data. But then you have to be careful about what your prior assumptions are. You cannot just go blindly and take a Dirichlet process out of the drawer and apply it to your data and think that you're going to get the universal solution. So you still need to think hard about the prior assumptions of your model. Although this is non-parametric, it's not going to solve all your problems. Okay.